Hey everyone, it's Mr. Wolfe here, and we're gonna be starting Unit 5 by going over Target 1 on Newton's third law. So before we begin, I just want to do some quick review on what a force is. So a force is just simply going to be a push or pull. It's going to be a vector quantity because it has magnitude and number, but then it also has a direction to it, whether it's left, right, up, down, or maybe even subtripetal. And then the units are going to be in newtons. Right. So before we get into defining the actual law, I want you guys to do a demo. So hopefully you have some force springs out on your desks. And I want one person and so first of all, you're going to take the force springs and you're going to kind of clamp them together almost like they're a rope like this. You're going to have person A, and then person A is just going to hold one of the force springs right here. And then person B is also going to take a force spring, but they're going to try to actively actually pull the spring. So the question is well, what's the reading on these scales going to be? So before you guys actually do the demo, make a prediction. So after you've made a prediction, actually run the demo, see what each reading is for the spring for person A, the spring for person B, and then write your results in the table. So as you continue to play this video, you should have done the demo for the force springs at this point. And it doesn't matter what exact value whether it was like 10 newtons, 25 newtons, what you probably noticed is that the value in each spring was exactly the same. So I'm just going to say that my reading in my spring was 10 newtons right here, and in the other spring, it was 10 newtons as well. And my guess is that this usually goes against most people's intuition because person B is obviously actively pulling it. Wouldn't you expect for them to experience a greater force, or at least to have some type of unequal forces? Well, it turns out, according to Newton's law, that every force has an equal and opposite force. So that explains why, in this case, that we had equal forces. They're also going to be opposite as well. Another way that will be really helpful for identifying these force pairs and for drawing things out is to draw almost like a free body diagram with our two objects. So in this case, I have person A, or there's a force on person A. By person B pulling them. And then there's a force on person B. And notice how this is just the reverse. By person A pulling on them. And then one thing I'm going to do just to show that these things are equal, because if you notice this line's a little bit less than the other one, is I'm just going to draw these congruent lines. This shows that, I've definitely made these lines to be equal on each other. All right, so we could apply the same exact idea to different objects as well. So let's go over maybe two more examples. And here we have someone pushing on a wall. So I'm going to say force on the wall by person. And then as a result, there's a reason why you don't continue going forward even though you're pushing the walls. The wall's pushing back on you too. So I'm going to say force on person by the wall. And again, these are going to be equal, so congruent lines, and opposite, so different directions. All right, so I'm going to come up with another force pair example for a hammer hitting a nail. And so as you hit a nail with a hammer, it's very obvious that the nail experiences a force, right? So I'm going to just draw on the sides because we have more room here. There's going to be a force on the nail by the hammer. But if you think about it, when you are hitting the nail with a hammer, you're driving this hammer down, right, with a bunch of speed, and then all of a sudden that hammer just stops. The nail also exerted a force back on the hammer in order for that hammer to stop. So there's a force on the hammer by the nail as well. So you'll notice a pretty easy pattern with some of these is that, it's just really going to be the reverse for each one, right? Force on hammer by nail, force on nail by hammer. And I want you guys to try out a couple examples on the next page. So it looks like this. So flip it over and pause the video really quick and go through this worksheet and then start playing it once you're done, and we'll go over the answers. So at this point, you should have completed the back side of that worksheet. If you haven't, make sure to press pause. Right? If you have completed the worksheet, keep on viewing. And here's what I have for that back side of the worksheet in terms of just identifying my force pairs. And some are going to be a little bit more difficult than others because it's just a little bit less intuitive. So let's look at the first one. We definitely have a force on the moon by the Earth. That's why the moon orbits the Earth, is that the Earth is always pulling on it. But the moon also exerts a force on the Earth as well. So force on Earth by moon. Not only that, but they're also equal. And in terms of how we can observe that the moon exerts a force on the Earth is the tides. The reason why we have the tides go in and out is because of the moon pulling on the Earth and on the oceans. All right, so for my example 2, this is going to be more of my objects are still, but remember, like the idea with the normal forces, you could still have an object be still and exerting a force on each other. So here I have a book resting on a desk, and so the desk is going to be applying a force on the book by the desk, and then as a result, you're also going to have a force on the desk by the book. And you know, if we went down to the atomic level and actually looked at the desk, it would be bending a little bit. Ever so slightly, showing that, yeah, the book is definitely applying a force on the desk. It's very similar to kind of like our ruler example where it bended, or even our laser on the table example where we saw that dot move as well. All right, so if we look at situation number 3, here our person is above the ground, but just when you jump up in the air, the Earth is still exerting that force of gravity on you, so I have the force on you by the Earth. And this one seems very unintuitive, but we know it's there because according to Newton's first law, there always has to be an opposite and equal force. But believe it or not, is that you are applying a force there's a force on the Earth by you as well. This doesn't mean like when you're jumping, it's not only when you're jumping. Right now, and as you're sitting in your chair, you are applying a force on the Earth, just like the Earth is applying a force on you. And again, that seems really unintuitive because it's very easy to see that the Earth is applying a force on you, but very, very difficult to see that the Earth that you are, in fact, also applying a force on the Earth. So we'll go more into that in a little bit in terms of why that is. All right, so let's look at scenario 4 right now. So this is actually what causes a car to move, is the tire starts spinning, and there's a lot of friction, right, between the tire and the ground. So the tire exerts a force on the ground. So force on the ground by the tire, and as a result, the ground also exerts a force on the tire, and this is the force that's going to propel that car forward in this case. And if we look at situation 4, it's going to be very similar to our car where we have and if you think about at least when I'm sprinting, and if I'm trying to run really, really fast, I try to push on the ground as hard as I can in order to propel myself forward, and this goes to our force pairs. So I'm going to be applying a force as hard as I can, so force on ground by my foot, and as a result, the ground is going to push on my foot. And again, they're going to be equal and opposite. All right, if I look at scenario 5, in this case, in terms of how a rocket's going to go up in the air, by the way, so eventually we're going to have electric cars and everything, and we're not going to have combustible engines, but when it comes to something like a plane or a rocket flying through the air, you have to have a type of gas due to Newton's third law. And so an example of that is that in the rocket, you ignite something within right here, the combustion chamber, and that releases gas at a really, really high speed. So there's a force on the gas that was in the rocket by the rocket. So the gas is going this way, force is going this way, and as a result, there's going to be a force on the rocket by the gas as well. And this is the force that's going to propel that rocket forward. And remember, they're equal and opposite. So, for these examples, again, it seems some of these seem really unintuitive. So, for instance, how are you applying a force on the Earth? Like, how are we? It doesn't seem like we are. Same thing, like, how is the ground exerting a force on us? What's going on there? To explain that idea, what I want you guys to do is, before we get to this example, go to my haiku page and watch the video that's labeled, I believe it's labeled Video Towel Boy. It's about a 30-second video from one of my favorite movies, The Water Boy. Watch it, make some predictions, and then come back here. Right, so at this point, you should have watched the Water Boy towel video. If not, make sure to pause it, continue watching. If you have watched it, continue on with this video. So when we watch that video of the linebacker hitting the towel boy, it absolutely seems like the towel boy is getting the bigger force in this case, right? He goes flying. But according to Newton's third law, it says that the force on the linebacker and on the towel boy are equal. And that is still true for this case. So I'm going to draw my force pair interactions. So the force on, in this case, the linebacker by the towel boy. And then there's also going to be a force on the towel boy by the linebacker. I'm going to draw my force pair interactions over here as well. I'll do abbreviations. So force on towel boy by linebacker, and then force on linebacker by towel boy. By the way, we know that there is a force on this linebacker because this linebacker was going at a very high speed before, and even though he still is moving, after he hits the towel boy, he has slowed down. And we see the same exact thing in the video, not just in this drawing as well. So we have our force pairs drawn out. We know that they're equal because this is what Newton's law says, but in our mind, this does not make sense, right? The towel boy absolutely experiences more pain. It seems like he's experiencing a greater force. Well, it turns out that what we're observing is not the greater force. It's actually going to be a greater acceleration. So we could reason through that by doing proportional reasoning with my equation right here. So again, according to Newton's third law, forces are going to be equal. We saw that with our force springs, right? Even though it may have seen that person B was going to exert the greater force, we saw the exact same force in the springs. Same thing is going to apply in this case. So to show that, I'm just going to box in my force. And this is just a way to visualize that it really can't change. However, we know that the variables on the opposite side of the equation, they might be different compared to the linebacker versus the towel boy. So this is what I mean. Force is going to stay the same, but the mass of the linebacker is way bigger. So to show that, I'm just going to draw a bigger M in this case. And the force on the towel boy is going to be exactly the same in terms of its magnitude, but the towel boy has a smaller mass. So I'm going to draw a smaller M to show that. All right, well, if both of these equations are going to equal the same force at the very end, well, in that case, the acceleration of the linebacker has to be smaller because I have a bigger mass here to equal that same force. And for the towel boy right here, since he has a smaller mass, in order to equal that same force, he's going to have a much larger acceleration. In other words, he's going to speed up a whole lot faster, and that's why he goes flying. He has a larger acceleration. So it turns out that they both experience the same force, but due to their differences in mass, the towel boy experiences a greater acceleration. So before you guys, one last thing is I want you guys to apply that same idea to the concept of applying your foot on the ground to propel yourself forward when you're running. So answer the question right here based on what I just went over in the video, and thanks for watching.